Good morning, good afternoon, or good evening, depending on where you are in the world, and welcome to today's Aviation Week webinar, Aerospace Leaders Discuss the Industrialization of Metal AM. This is sponsored by Velo3D. I'm Ed Hazelwood, and I will be moderating today's event. We have just a few announcements before we begin. The webinar is designed to be interactive. The dock of widgets at the bottom of your screen will allow you to learn about today's speakers, download resources, and participate in the Q&A session that takes place at the end of our presentation. The slides will advance automatically throughout the event. You may also download a copy of the slides at the end of the presentation. Towards the end of our webinar, we will ask that you complete our survey. It's found on the right-hand side of your screen. Please take a minute to fill this out before leaving us today, as your feedback will provide us with valuable information on how to make future events even better. Lastly, if you are experiencing any technical problems, please click the Help widget found at the bottom of your screen, or type your issue into the Q&A area, and we'll be glad to offer one-on-one assistance to you. Now, on to the presentation. Aerospace leaders discuss the industrialization of metal AM. Discussing the topics today are Brian Ballman, the manufacturing chief engineer at Honeywell Aerospace; Laura L. Eli, she's the director of programs at the Barnes Global Advisors; Max Hout, founder and CEO of Launcher; and Dr. Zach Murphy, Vice President of Technical Partnerships at Velo3D. To learn more about our prestigious panel, be sure to read the impressive bios about today's presenters within the speaker widget. So, ladies and gentlemen, it's time. Let's get started.
Hi. Hey, Matt. Hey, Ed. Hi, my name is Brian Bachman, and I'm Chief Manufacturing Engineer at Honeywell Aerospace, and I've been part of additive manufacturing for 20 years or so, and I love it. Yeah. I have a video to start with to introduce myself and what Honeywell has been doing with additive. Hey everybody, Brian Bachman here, and today I'm at Honeywell's Additive Manufacturing Technology Center, and we have a big facility with over 20 laser powder bed fusion printers that our engineers are using every day. And we're using it to make some very complex geometries that help improve our designs, take out weight, and help with speed to market, getting things faster. Additive's so great at that. And so here's a really good example of one of those parts. This is a heat exchanger part, and if I were to cut it open and show you, it would look like this with so much complexity. You know, you cannot do that with any other method today. So join me, I'm going to take you on a tour of our facility, and I'll show you what this process is about. So the type of additive that we do in this facility is called laser powder bed fusion. It works by fusing metal powder particles into the shape of a three-dimensional model. And it starts by laying down a very thin layer of metal powder. Laser beams are used to scan the pattern of the part, and this energy fuses the powder together to the layer below it, over and over, layer by layer, until we print the full geometry of the model. After the printing is done, the powder is vacuumed out and sent to be sieved before it makes its way back into the machine. So all of the unused powder from this process is recyclable. The powder that is inside the parts is shaken out using dedicated equipment. For some geometries, getting all of the powder removed from inside the part can be tricky. The parts themselves are stress relieved in a furnace, and then we cut them off the build plate using an EDM machine, or electrode discharge machine. We remove metal supports and then we scan the parts to make sure that what we print meets dimensional requirements. And so that's our process. And it's not just about what Honeywell's doing internally with additive manufacturing. We're also working with several outside suppliers who specialize in 3D printing. And we are qualifying them to make Honeywell products using additive manufacturing. So it is together with them that Honeywell is creating the future of manufacturing. Thank you. So yeah, thank you for that overview, and I hope you enjoyed that video. Honeywell's doing a tremendous amount, and we've been doing it for many years. And the part you saw in that video is an actual approved part for production commercial aircraft. Right? So we have it flying today. So it's real, it's very real here at Honeywell, additive manufacturing. Thank you.
Thanks, Brian. That's awesome. And unfortunately, I don't have a fancy video. Most of the work we do, we don't get to talk about too much. But I'm Laura Eli. I'm with the Barnes Global Advisors. When I describe my role, I describe it as operating an intersection of technology, people, and strategy. I'm a metallurgical engineer with 17 years of manufacturing experience, including technology leadership team building, putting a next generation of metallic technologies like additive manufacturing and friction stir welding and working to put those on airplanes. I'm now the director of programs at TBGA, and my role is really just to help lead the team to foster strong relationships and deliver maximum value. When we think about AM in general, but AM in aerospace, it's hard. And our job is to help make that a little bit easier as people are looking to navigate. So we work with customers from small startups to large OEMs to the DoD. We're an independent and technology platform agnostic group, and we have 3 areas that we primarily operate in. We have advising, which is our consulting portion, training, where we have comprehensive live training, as well as an online certificate with Purdue. We've trained over 1,200 people through our courses so far. And then a communications group where we help customers tell their story, make connections, and drive awareness. I thought it might be appropriate to round out a bit of the conversation here, as we're going to see some awesome examples and conversations from all of the guys on the panel here with flying applications. So I'm not going to spend a lot of time on these, but if you haven't looked at AM in aerospace that's out there and flying around, this vent that NASA put on the Orion capsule, a bracket with RUAG Aerospace that Morph 3D produced, titanium bracket that Arconic, now Cumberland Additive, has put on with Airbus and flying. I think it's also appropriate to note, I think we're mostly talking about metal AM today, but there's a lot of flying polymer AM as well. So this is an example of ducts that are flying with Boeing with Stratasys processes. Another area that I wanted to give some airtime to, because anyone that knows my background, I do love directed energy deposition. It's where I got my start. So here's a few examples of flying directed energy deposition applications. And you'll note that, there's a step change in size here with respect to what you can do in powder bed processes and then some of these DED processes. So we have flying 787 floor grid galley components that Norsk Titanium did with Spirit and Boeing on the 787, F-15 pylon rib that was decades ago that Kevin Slattery on our team, who's now retired from Boeing, was a lead engineer. That's a laser blown powder process. The center one is Lockheed Martin. They did Siaki's electron beam wire to do propellant tank domes. And the final one that I'm showing there, and we'll see quite a few of different ones around rocket and rocket nozzles and rocket engines with Max's presentation. But this is I think it's about an 8-foot tall rocket nozzle that GKN Aerospace deposited Inconel 718 on the top of it for Ariane 6 rockets. So AM comes in all different shapes and sizes. And here's a picture of me just to give you a feel for some of what we're talking about in size and depth. This is back during a supplier acceptance test with some DED equipment. So DED is where my heart lies, but I have space for all AM processes, and we're seeing tons of adoption across aerospace, including in urban air mobility with people like Joby Aviation and their electric VTOL saying we're going to use additive manufacturing for safety critical parts. and across the space. I knew I was going to end up saying that at some point. But we're going to hear a lot more from Max, and I think people there, it's so ripe for disruption. So all of these applications have a set of requirements, and one word that you're going to hear me repeat through this conversation is the word trust. And trust is not just about relationships. It's about supply chain. It's about a whole lot of underpinning data as well as historical performance. So I'll hand it on over to Max.
Great, thank you. Good morning or good afternoon to some of you. I'm Max Out, founder and CEO at Launcher, and I'd like to thank everyone for being here. So for a quick introduction, Launcher is an aerospace startup based in Los Angeles, and we are end user of additive manufacturing. So what we are producing is an orbital launch vehicle or a rocket, more simply, to deliver our customer's satellite to orbit. This is an illustration of the first product we are building, Launcher Lite. It can carry up to 150 kilograms of customer satellite to low Earth orbit. So it's a very small, but obviously commercially useful launch vehicle. And our goal to reach orbit with Launcher Lite would not be possible at all, especially with our funding goal, which I'll explain in a second, without the availability of 3D printing, especially for our turbopump and combustion chamber of our engine. Launcher's goal, two key differentiators. One is to have the highest performance, more launcher. Highest performance mean more payload. And the other goal is to reach orbit with a total $50 million invested in the startup. And that would be a twofold improvement from the current record. And this is only made possible with the ability to use and leverage 3D printing for key component so that we don't have to do tooling, casting, spin forming, brazing, and so on to develop our high-performance liquid rocket engines. The cornerstone to what we are developing is this is an illustration of our E2 liquid rocket engine. It's a 22,000-pound thrust liquid oxygen kerosene engine. It's closed cycle, so highest performance. And the two key component is a combustion chamber, which is fully 3D printed in copper alloy, and the turbopump, which all critical parts are also 3D printed with Velo 3D here in Inconel and aluminum, with some CNC machine part, which are easy to produce, such as a shaft. Our launch vehicle and our team is in full development with most of the advance towards our goal to have our first launch in 2024, being with the engine. So what you see here is the liquid oxygen turbopump for the E2 engine. It's on its test stand at NASA Stennis. We partner with NASA for testing. It was entirely, the liquid oxygen part on the left was entirely 3D printed with powder bed fusion process, as we discussed. The outlet is in Inconel, the rotating component are in Inconel too, so impeller inducer, all 3D printed using Velo 3D. And the inlet, which is lower pressure, is in aluminum, also 3D printed. And in the video I'll show you in a minute, we'll see the test. Moving on to the other key part of the liquid rocket engine is the combustion chamber. And so Launcher 3D printed combustion chamber subscale. So this is about 1,000 pounds of thrust. And we performed more than 140 tests and iterated many times on the design, even material switch from Inconel to copper alloy, to basically get to the point where we reached 98% combustion efficiency. We innovated using liquid oxygen regenerative cooling instead of RP1 to reach that efficiency and reach all of our goal subscale. We probably produced about 30 combustion chamber and injector to get there in 140 tests. And that was only possible to do thanks to the speed and the ease of iteration made possible by 3D printing. And then the next step, sponsored by Space Force SBIR grant. Last year, we scaled up to the full scale. So this is the actual combustion chamber size and material that will be flying on Launcher Lite. And this is at NASA Stennis on its test stand. It doesn't have the turbopump, so this is there for a pressure-fed component testing. And you can see that was our first test last October. where we haven't yet reached the point where we can replicate the blue plume you saw on our subscale test, which is a testimony of the combustion efficiency. But this summer in July, we have 3 more tests with 3 more combustion chamber in copper to basically get there as part of our development. So now a quick video of some of this testing and development, and then I'll be done. Oh. Sorry, let me... So all the 3 test clips, in this video are powder bed fusion 3D printed parts. The first one was our subscale test to the highest performance, 98% efficiency. The second one was the turbo pump test, and the third one was the full-scale combustion chamber, the first test. Thank you, and we look forward to have the discussion and the Q&A.
Thanks, Max. It's always a difficult one to follow when you have rocket engines actually hot firing, but I'll do my best here. My name is Zach Murphy. I'm the Vice President of Technical Partnerships and Sales at Velo3D. Velo3D, if you don't know us, is a manufacturing technology company. We work in metal additive manufacturing and specifically laser powder bed fusion. So I'm kind of the counterpart to Laura and her love of direct energy deposition. My love is truly laser powder bed fusion. We make the most advanced laser powder bed fusion systems on the market. It's a vertically integrated solution that goes from the initial software or print preparation software, which is called Flow, through the machine that you see here in the video, that is the Sapphire printer, the Sapphire family of printers, and then to a quality assurance software. And I think just to echo what Laura was saying, the 2 things that we really see as our critical deliverable to customers are the capabilities associated with metal additive and the geometries that you can print, and then really the trust of the part itself. And so with those 2 things, we kind of have our fundamental value proposition. And that's really where Velo can contribute the most to metal additive and to aerospace specifically. Ed?
All right, Max or Zach, thank you very, very much. So before we begin our Q&A session today, please once again direct your attention to our webinar survey. It's available on the right-hand side of your presentation window. If you happen to close the survey, you can simply reopen the widget by clicking on the clipboard icon down at the bottom of your screen. Or, and I'd like to thank you in advance for filling out the feedback form. Participation in the survey, as I said before, lets us do a better job on all future webinars for you. So now we're going to get into the Q&A portion of our event. As a reminder, to participate in the Q&A, just type your questions into the Q&A icon at the bottom of your screen. And if we cannot answer all of your questions during the webinar today, we'll be sure to share your questions with our speakers so they'll be able to reply to you later offline. So first off, I'm going to toss out to you guys, and why don't we start with Brian? So I'm going to ask you to answer first, but then everybody else can jump in. So we'd like to hear how you think aerospace culture needs to change in order to adopt additive manufacturing on a larger scale than we see today. I'd like to hear also your experiences in dealing with aviation customers, as well as regulatory bodies that you have to deal with. So organizations such as FAA, Army, Navy, DoD, DARPA, etc. So Brian, if you would start, and then everybody else jump in, please.
Yeah, thank you, Ed. So getting acceptance is such a big deal for additive manufacturing, right? From the end users to the customers and the regulatory bodies, Honeywell spent a lot of time investing in the technology to build the confidence required by those sources, right? There definitely is in the aerospace industry, conservativeness, right, with accepting a new technology such as additive manufacturing. People want to see data, and they also want to see control. They want to see quality from your process. And so that's something that we work on a lot. We invest in making sure that we understand the process. We invest in understanding the machines, the quality that comes out, to show the regulatory bodies, the customers that are putting aircraft parts into their aircraft that we have control over this process. So I think that's a really good point to make, that is not just printing a part and putting it on an aircraft. There's a lot that goes into changing the culture. And I think it starts with data and understanding.
Okay.
Yeah, another bit that I'm going to pop in. Another bit that I'll add to that is I think that depending on the types of groups, sometimes the product development life cycle is not really aligned to new technology or what additive brings to the equation. So along with organizational structures and knowledge of different players. So it's something, and again, people and knowledge will be something that comes up multiple times with me anytime you're looking through it, because when we talk about industrialization of AM, you need pervasive knowledge. It needs to be known as well as other manufacturing processes across the board, whether it's the certifying authorities or the design authorities or the people that are making that, the quality people, supply chain, everywhere. So I think some of the aerospace culture change for additive is also just a knowledge gaining mission for it. It's the same qualification process, same certification process. However, we all know that it's not that simple. Additive has its own unique things, and so figuring out how to address those and adapt those with that underpinning data that Brian just talked about is hugely important.
From our point of view, I think the main transition will take time, and it needs a new generation of products and a new generation of designer and facilities. So for example, at Launcher, if we had the ability to do our combustion chamber in-house the traditional way, we had all the tooling from spin forming and CNC machining of the part and brazing, maybe we wouldn't need and we wouldn't want to switch all of that to 3D printing. The reason we are using 3D printing is because we wouldn't even be around without it. That's what reduced the barrier of entry and allowed us to print, complicated geometry combustion chamber with hundreds of cooling channels without the need for this tooling investment and this know-how. So, so we're an example, for example, of a new product and a new team where we're not transitioning. That's just the only way we can do it. I think within existing companies and existing products, I would say why transition? But over time, I think you'll see designers that's their first go-to anyway. I'm talking about graduates today that will be experienced designer in 10 years. And you'll see facilities that are starting with the additive capability and are supplementing with other, whether casting and spin forming and others, only when they can't use additive. So that's our point of view, is that there is a time element needed for the major shift. But for new product and new team, I think it's already happened. Everybody is leveraging it.
Okay, Zach?
Yeah, no, I would really echo what Max said, right? Which is that there's certainly some things that you have to address as you're moving older products into a new manufacturing technology that require kind of a different way of approaching it. And you really do need to gain confidence in the manufacturing technology. But we absolutely see that, especially for new products or new revisions of existing products, being able to leverage additive is the fastest way to get through the development cycle, and you can also start to improve the performance by leveraging the capabilities. So it's exciting to see what some of the new generations of designers and engineers are coming up with this extra tool in their tool belt.
All right, so one of our viewers today works for an NDT inspection laboratory. And he says he's been focusing the efforts there on inspection of AM aerospace parts. So he would like to know, how has NDT testing and inspection helped or hurt the advancement of your operations? Why don't we start, Zach, with you? We'll go backwards this time.
Yeah, so it's an interesting question from our perspective, because as a manufacturing technology company, our goal is to give customers the tools that they need to have confidence in the quality of the printed part at the end of the day. And that's kind of I think the critical deliverable, especially in aerospace, right? Where you're talking about kind of your confidence intervals in the quality of the part. So NDT traditionally has been really more of a post-process technology, but one of the things that we're really focused on is building inspection and metrology capabilities into the equipment, so that while you're manufacturing the product, you get a lot of data that's actionable and intelligent and allows you to have confidence and hopefully at the end of the day reduce the requirements around both NDT and destructive testing or witness samples and other aspects of the qualification. But I think that's a really good question for somebody like Brian or Laura, who have a lot of experience in kind of the qualification of aviation and aerospace components.
Right, Max, you want to jump on next?
Yeah, I'm happy to share our experience. So, we do obviously our goal is lowest cost. So we only do any process, post-processing or inspection process if we have to. We're not yet dealing through a regulatory testing or qualification process. So in practice for us, it obviously means material testing on coupon on the build plate. We do that as a matter of fact. And for example, the outlet in Inconel printed on the Velo system, we were really positively surprised at the quality of the material, which beat our expectation. And then the second big challenge that's related to the combustion chamber, because we have internal cooling channel, and because of the process of laser bed fusion, where basically the laser goes around to create the walls around the cooling channel, so the powder is trapped inside this cooling channel. We've had challenges where one of our tests failed because we had three cooling channels that were clogged, and at the time we had no access to comprehensive CT scanning. And so on the next iteration, we obviously had to add this step, and we found a partner, and we're able to CT scan our full-size combustion chamber to a point that I would call it magic in terms of the data we were able to see inside each of these tiny cooling channels, hundreds of them, and confirm there was no powder. So that's more our approach at this point, because we're not jumping through regulatory or certification loops. So it's more, what do we need to do for the part to function? And right now it's material testing on coupon and CT scanning for internal geometries to make sure there's no powder.
Laura, let's go to you.
Yeah, NDT is interesting because, like many processes, it's been well developed for other manufacturing processes. So sometimes when you go to apply it to AM, you get different results. So assuming that what you look for in castings versus a laser powder bed fusion part, for example, there's going to be different types of things that you're looking for. So I think people are coming up the learning curve there, but I think as Zach started to alluding, you need to understand your defects as well as your ability to inspect from them at the beginning of your process development. So understanding what your qualification plan and what your likely inspection process is when you go to actually qualify these parts, and prove this to a certifying body, you have to take that into account up front. It cannot be, oh, I made my parts. Oh, shoot, now I got to go see if I can see any defects in them. So obviously, planning from the beginning to really understand what you're doing from a qualification standpoint is really important. And another note, it sounds like the question came from an NDT provider. From my personal experience, NDT providers that are arming themselves with an understanding of additive manufacturing materials and looking at parts and being able to be an intelligent supplier to people that are looking at their parts is a huge deal. Because I certainly have had analysis from metallurgists on AM parts that were just completely incorrect, and it had to do with them not understanding that it was an additive manufacturing process. So anything that you can do to bring value there, and I know that the standards and specifications are lagging a bit in this space, but they are making progress.
Excellent. So Brian, we'll come over to you now.
Yeah, so I'm hearing a common theme. We look at NDT and inspection to pair, and we combine it with the qualification, the understanding of the process, and that's very true. And we do many different types of inspection, fluorescent penetrant inspection. We do X-ray. Some parts do CT scanning. We have done ultrasonic on others. There are many different methods. We choose them depending on what we're trying to inspect for and the type of part and the geometry. So I think, there are challenges there. It's not that easy. You can't assume that you can just, like any other manufacturing process, apply these methods without taking certain steps. Like, for instance, a lot of times we apply penetrant inspection on the surface of additive parts, and that requires to get the surface to an inspectable condition for that type of NDT. And you need to put some post-processing into these parts, right? And that's the funny thing, is a lot of people talk about printing, but printing is, in other ways, people describe it as the easy part of the process. It's the finishing that's the difficult, the post-processing, getting the part to the finished state so it can be inspectable. And we put a lot of emphasis on that. So there's definitely a lot of work being done here at Honeywell on inspectability and figuring out the best way to do that.
Okay, thank you very much. So Brian, we're going to stick with you for a second because I have a question from a viewer who was specific to you. And he asks, please describe your process to qualify parts for flight. And once a part is qualified, do you only then print it on a specific machine?
Okay. There's a lot in that question. Oh, boy. We do a lot to qualify our parts, right? And it definitely starts with understanding the underlying material that we're printing. And then we bring in the machines that we're using to print that part. And they can be multiple machines. So we try to be machine agnostic. Look at all different types of technologies and then bring them into one centralized understanding of the material properties. I think that's an important point to hit on for us in the terms of qualifying additive parts, right? There's a lot we do, but at the basis of it is understanding the printed material, the properties that it gives you, the strength, the density, the chemistry, all that. I think, a lot of people don't really understand how much work goes into characterizing the material properties, right? I mean, you do some tensile data, you do some fatigue data, but sometimes it's just like a small subset. We need mountains of data. We will spend probably over $1 million just to characterize one single alloy for printed additive. And so there's a lot of work that goes in the underlying processes, the foundation. But when we get into specific part qualification, then we start building on that foundation. We look at the specific part, how we build it. We'll take test samples from that part. We'll take that part and we'll put it in test rigs. We'll do validation testing on it. And there's a lot that goes into it. Probably too much to explain in this webinar.
All right, next question probably goes to Zach. So this is a Velo3D specific question. And a viewer says that he's seen that Velo3D flow software is capable of adjusting processing parameters based on the different features of a part. So things like vertical walls, thin walls, etc. And it looks like the software kind of does that automatically. So this person's wondering if it's possible for the user to specify what kind of properties are wanted in certain areas of a part.
Yeah, it's a great question. I think that's one of the things that really sets Flow apart as a print preparation software. It's designed so that the user can express the intent of what they're trying to do, right? So it's kind of a goal-oriented piece of software, and you can basically say, you know, I want this surface to be a very high-quality surface, or I'm going to machine this after the fact, so I don't necessarily care as much about what the surface finish is. There are different sub-features that you can apply processes to optimize for kind of the properties that you're looking for. And I think it's a very intuitive interface to do that. And the reason that that's really important is that the process itself, kind of the behavior of the melt pool when you're making the material, is very much dependent on the surrounding material, right? The powder and the solid metal that exists in the immediate vicinity. And so it's kind of a boundary condition problem. And what our software does automatically is take into account those variations in geometry and the subsequent behavior of the melt pool and the solidification of the material in order to basically ensure that, that you're able to print this much wider range of geometries than you could with other technology.
Okay, thank you, Zach. Laura, let's jump to this next one. We'll start with you, but we're going to probably do a round robin on this. And the question is, what's the current state of material standards for AM parts, and how do you assure material properties for customers?
Yeah, absolutely. The great news is a lot of work and development in this space. And I think this is another area that just shows the maturity of the industry. The other thing that it requires is collaboration, which means people actually, you know, different companies that sometimes are competing for, you know, for customers need to come together and say, what does good look like here? So I feel like this is, you know, there's multiple materials across, there's DED specifications, we have, you know, obviously multiple powder bed, multiple materials. One of the things that is going on that I am excited about is we're starting to see more of like data consortiums forming to develop things like specification minimums. So while they might not be at full MMPDS, you know, design allowables, there's a whole nother conversation of whether that's even possible with everyone's different machines and processes and combinable data. But just at the bare minimum to say, let's get enough data to say what a good specification minimum is just to start the design process. So SAE, ITC has an additive manufacturing data consortium where they're pooling groups together. Some people are bringing in their data, they're developing data that's not there. All of these things are showing a level of maturity because almost everyone will say, okay, start with this specification and then I'm going to have my own special additional requirements that I add to that. But at least as suppliers, people that are supplying to multiple customers, if you at least are starting with a first master specification, that's a lot easier starting point than having something that's completely customer unique every single time.
Max, let's go to you on it next.
Yeah, from our point of view, you know, we usually work with either our service provider or the machine manufacturer to get expectation on material qualities, you know, in relation to obviously the classic, you know, the classic material that has not been 3D printed. Also, we've developed our own heat treatment and HIP process with these vendors. So at the end, we end up with an expectation, and we do coupon with our first builds, and that gives us a benchmark. And then as we go forward and print more serial number or more iterations, we verify against these. So we've not yet been involved with requiring our service providers to adhere to our standards. And obviously we're in development, so our customers are not yet requiring that from us.
Brian, you want to take a shot at that?
Sure, yeah. I mean, like I spoke about, Honeywell does a lot of testing ourselves, and I heard Laura say B-basis and then PDS, and that's a big thing for us. So we do a lot of validation testing, right? After we've already gotten to the point of establishing B-basis material properties, right? We have that mountain of data, and then when we go in and we make sure that we're doing that appropriate testing, we do every build for production, we do lot acceptance tests, right? So we do coupons every part build that we build for production, for commercial aerospace, for defense. Everything has samples built in it that get tested, every part.
I'd like to chime in here too a little bit. Just on I think that the manufacturing technology companies also, to be honest, have done themselves a bit of disservice by not focusing on giving customers pedigree data that could allow them to actually get to this conclusion much faster. So, I don't mean to kind of throw down the challenge here, but I think that people who are making the process and people who are making the technology and the tools that are then being used by the industry have some responsibility in helping their customers be able to get to these design allowables. And there's a lot that can be done there that can actually accelerate adoption throughout the industry, because of every single company that has these tools has to do their own qualification and develop their own data sets that allow them to get these confidence intervals, then it's going to waste a lot of money and it's going to waste a lot of time. So we're at Velo3D working really hard to short circuit that in every way that we can, especially for these aerospace components.
Laura, let's toss this next one over to you. So other than single-use parts, what class of multiple-use, high-performance aerospace parts are in production now?
Yeah, so from an additive manufacturing standpoint, there's actually quite a few. Some of the ones that I showed on the previous slides are a few of those examples. So if we start with the aerostructure side, primarily we're talking statically loaded components. However, that floor beam bracket is an example of that. However, I know that the folks at Boeing and Spirit and Norsk are working really, really hard to move those to fatigue and dynamically loaded applications. And I will certainly tell you from my DED background, like the business case on those closes every single time. So there'll be, once the technical veracity is there, I think we'll start to see more of that. But I will point from the aerostructure side, that F-15 pylon rib, that was a dynamically loaded component. I mean, you're holding portions of a wing together with that pylon rib. So it is possible and it has been done. It's just that burden of proof and those requirements and the stability of the processes are quite significant. From an engine structure standpoint, there are, particularly in the commercial market, there are definitely multiple applications of AM parts that are being used over and over and over and over. So GE obviously has a few applications of those with fuel nozzles and some other things. So we're seeing it more and more. MRO space is growing. However, that's tough because a lot of times it's like one part here, one part there. It's hard to Max's or to Brian's point. It takes $1 million to do the process development for one material. It's going to take some time to get to that. So the other thing you'll see with, whether it's Max's space or even in like SpaceX, when you're talking reusable rocket space, this isn't just a one fire thing, right? They've changed the game. We are now landing and, shooting these things off again. And there's AM that's quite pervasive through, the larger rocket space as well. And those are multi-use type of applications.
So Max, since we just sort of got off of the rocket thing here, why don't you give us your perspective on that? And then after that, I want to jump to Brian before we go to Zach. So.
Yeah, I think we're in the early stage of development, and reusability will obviously be a part for engine. Small vehicles are typically not reusable, given that the mass budget that are there. But our E2 engine is absolutely reusable, and that will be a part of the longer term development of the product to ensure that it can meet with AM part the reusability requirements.
Brian, you're up next. Give us a Honeywell perspective, please.
Well, as far as the type of parts we're putting additive on, it's a whole range. I think, we publicized one application, which was for a really old casting part. So it was a part conversion that we struggled to get from a casting supplier, and we were able to print it with additive and put it into our engines, keep the product moving and make our customers happy. And that was a critical application. It was a turbine bearing house. It was a wear bearing housing, right, for a propulsion engine. And it was a critically loaded structure. So it was really important that we understood what we were printing, that we felt confident putting it in that type of application. But that would what we would call a one-for-one application. You have an existing part, and then you're replacing it with additive. And that does happen, and it helps our supply chain a lot when we can find those opportunities. Outside of that, we are using additives in some really cool things, with new designs, and we're trying to embed those into the right applications. I can't really get into all of them right now, but they are some pretty amazing things, and it just makes me excited every day to come in and work with this technology.
Thank you. Zach, so I'm going to go to you, but I'm going to toss another question at you too, because I think these are kind of related. So one of the viewers asked, will generative design and underlying physics soon lead all designers of certain products, such as rockets and turbine engines, to arrive at optimized designs of essentially interchangeable morphology?
So I don't know that the end of the question is really clear in what it's meaning, but I think, from an engineering perspective, your goal as an engineer is to design the best part for the application, right? To kind of co-optimize all of the competing aspects of performance, speed, cost, and deliver, a really highly optimized solution. Generative design certainly plays a role in that, and I think generative design, as it relates to additive manufacturing, they have to have evolved together, because a lot of parts you could make with generative design weren't necessarily manufacturable before AM, and they're also extremely useful in capitalizing on the benefits of AM. So I definitely see more generative design coming in the future. I think specifically, around structural components and other areas where you can really define your goal functions well. It makes a lot of sense. At the same time, there are parts that are probably not kind of what you would think of as generative design that are really great applications for additive. And I think what you see in the launcher turbopump is kind of a really good example of that. It doesn't necessarily require this, crazy organic, topologically optimized generative design to be the best part for the application.
Laura, let's take you next on that, particularly focusing on the generative design part of it.
Yeah, absolutely. I mean, I think a lot of what we see is generative design is also great for influencing the design. Often you'll see a very interesting component, but then perhaps we need to reflect on additional requirements that we didn't manage to put into the generative tool. So what we see a lot of is you kind of have a conventional manufacturing approach, something kind of middle of the road, and then a very far out generative. But we see a lot of components, particularly in aerospace, if you look at aerostructure and some of the different ones that are at very least influenced by design. I think the other challenge that you have in aerospace, if you think of aerostructures, you need to be able to analyze it And in some cases, the FEA tools are not a level of capability and maturity to work with some of those generative designs. So that's where often you'll see those simplified. And one of those reasons is manufacturability. But the other thing is just the ability to actually analyze it and feel comfortable with its performance.
Yeah, I think, and adding on that, you know, at Launcher, we're looking at these tools for structural, but it's interesting to think about, you know, if you think about pumps, for example, or cooling channels, you know, it's unlikely that an AI at this stage is going to beat the design patterns that have been optimized for the last 100 years. Maybe they will, and there will be a watershed moment. But I think today that's not the case. So structural, it makes sense. But the real breakthrough of 3D printing, when you talk about pumps or you talk about combustion chamber cooling, is the ability to manufacture them, to iterate them without tooling and without, you know, incredibly expensive process that have low yield and require, you know, very specific know-how that can only be developed in, you know, in years or even longer, like a craft, like brazing combustion chamber, for example. So for us, it's the right tool for the right application, and you know, the breakthrough that we see in 3D printing, such as Velo's nose support technology, which have allowed us to print, you know, traditionally designed impeller inducer in one shot, print the first prototype, machine it lightly, you know, obviously heat treatment, and then test it at nominal parameter. And we met all of the requirement of the heritage design of this pump, but without any of the complexity and tooling to get this part produced.
Mm-hmm.
All right, Brian, do you want to tackle that? Then I got one for Zach after that.
Oh, yeah. I mean, generative design is great. I mean, take heat exchangers, for example, right? They give us so many great ideas for how to do different geometries, different ways of approaching that problem, right? But the end result doesn't always look like what you're actually modeling when you use these newer software, shape generation softwares and so forth. You know, obviously there are challenges with analysis that Laura pointed out, and what Max was saying about post-processing them. You have to look at the realities of what we have today to make what we're trying to make, right? But I love it. I think it's definitely helping us get to some new levels and take this technology to where it needs to be.
Okay. Zach, a question for you, asked specifically. What type of post-processing is required on the rotating 718 components after printing before they can be balanced and tested?
That's a good question. I think, you know, it depends on the specific requirements for the application, but a lot of times, kind of to Max's previous statement, you can do some surface finishing, some light machining. And I think that's, you know, that's one of the areas where Velo 3D has really shown some pretty good adoption. These impellers or shrouded or open wheel impellers, turbine wheels, other components like that are really great uses of additive manufacturing due to their kind of complex geometries. And I think you know, the E2 turbopump test goes to show that these rotating components made with additive are viable, because that's a question that a lot of people have, right? If you're spinning an impeller at many tens of thousands of RPM, is AM good enough? And the answer is kind of unequivocally yes, if you have the ability to kind of demonstrate and validate the quality of the components. And maybe Max can speak a little bit more to that as well, if he's actually qualified it.
About a specific experience, so one of the main advantages internally to our turbopump is a shrouded impeller and inducer. And you know, usually you would need on traditional 3D printing, you would need to put a lot of support internally that are very difficult to machine out, and you would need to print it at an angle, something like 45 degree, which creates issues with uniformity of the part. So with the Velo 3D technology, we were able to print it flat on the build plate. And we had heard stories of companies trying to do rotating component 3D printing, basically tripping at the balancing step. So, we obviously use a balancing shop that spins the part at 30,000 RPM, and then with a machine detect the amount of material we need to remove to have perfect balancing. And we came in with our first 3D printed impeller, and we balanced it right away. Very, very good data out of the balancing and very easy, meaning the amount of material to remove was trivial and within the allocation. So the other type of post-processing is, there's no support inside. So all of the flow paths are clean and with a very good surface finish, which are very important. We've done tests where we've honed one of the flow paths, and one we have it as printed. We've tested the as printed one and had amazing results in efficiency. But we will test the honed one. But again, we're trying to find the most cost-effective process. So if the honed version is not giving us material efficiency improvement, we will use as printed. We do some machining. We create a spline to mate to the shaft, and obviously the typical heat treatment and hip that you would expect. But it's pretty much as close as it gets to use a part as printed. What we've seen with this project with Velo.
Max, thank you. I'm going to switch questions now and jump to Laura. So we're going to so specifically, can you share more, Laura, on your thoughts on how you successfully get trust between various parties in the space? So it's like machine suppliers, designers, raw material providers, post-processors. How do you get all that to come together so that everybody's confident in everybody?
Well, just like many things in life, when you want people to work together, communication would be the #1 key. So I'll give you kind of a couple of examples. Within aerospace, a lot of time you have a design authority or an OEM. So if we go big, let's go with a Boeing or a Honeywell or somebody like that has a very large system. And then they have this whole maybe super tier 1, tier 2, tier 3, this entire supply chain that supports them. And so the biggest thing that a design authority can do for their entire supply chain is to communicate what they need and to communicate their plans and say, this is where we're heading. And this is what I need from you to support me to successfully put this product on a plane. And then you flip the script on that, and these supply chain needs to then go back and say, this is what I need. And in some case, that might be, I can't make this big of an investment unless I know that there's actual work there. So when it comes to building that supply chain, whether it's the technical or the business side, we still need a very collaborative approach, especially in additive, to be standing these things up. From a certifying authority standpoint, I'll give a great example. FAA and EASA have been doing annual open forums where they are coming together, and everyone is welcome to participate, but they're talking about these things. They're talking about certification paths. They're talking about how you're qualifying AM components and processes and equipment. So I think, those two things, I consider those two key pacing factors for AM, the certifying authority and the design authority, because if the design authority doesn't choose to put it, on an application, obviously it's not going. And if the certifying authority is not going to sign off on it, obviously it's not going to go. The final one that I'll say, and we already talked about standards, but it's come to the table and participate in those standards development. And that means, processing guys might need to talk on a materials one or on an equipment and a process printing one. The supply chain needs to participate as these standards are being developed to make sure that they're not being impacted by incorrect standards.
Okay, Laura, thank you very much. Ladies and gentlemen, unfortunately, we are just about out of time. A ton more questions I'd love to throw out to our panelists. But as we told you earlier, questions that weren't asked, we will submit them to our panelists, and they'll be able to reach out to you and answer those questions to you after the fact. So before we sign off, I would like to thank our presenters, Brian, Laura, Max, and Zach, as well as their sponsor, Velo 3D. Within the next 24 hours, you're going to receive a personalized follow-up email with details and a link to today's presentation on demand. It's the on-demand version. So please share that and invite your colleagues and peers who may not have been able to attend live today to listen to the event. Thank you very much for attending, and have a wonderful rest of your day.
Thank you.